summarize what we said, we showed that this law, the Faraday-Maxwell equation, is able to explain the theoretical, the experimental observations that we showed, whether you move the magnet towards the loop or away from the loop, or you keep the magnet fixed in space and not moving relative to the loop. It explains how a non-conservative electric field is created due to the change in the magnetic field in the area that's enclosed by the contour. So this equation is always valid. It's one of Maxwell's 4 equations. So that's why it's a very important equation to take in this particular form. So basically now we have 2 kinds of electric field then. We have an electric field due to static charges, which is a conservative electric field. If you integrate that electric field over some contour, integration of E dot ds around some contour, you get 0. But a non-conservative electric field, when you integrate E non-conservative dot ds around some contour, it doesn't have to be 0. It could have a non-zero value if the magnetic field is changing value at the elements of area that are subtended by this contour. Of course, you could have, maybe you could have a magnet here going upwards and another magnet here going downwards, and maybe their effects will cancel. So you might get some places in this area where this dot product is positive and some places where this dot product is negative, and so when you add up you could get 0. That could happen. So that's why you have to actually integrate this dot product over the whole area. You have to see what's happening everywhere, at every point on this area. So we want to rewrite this equation in a different way. This is the way we wrote it down. We wrote integration of partial b by partial t dot dA. But the question is, can we take this partial by partial t outside of the integration and write it as d by dt of the magnetic flux? Integration of b dot dA is the magnetic flux, right? It's phi b. Is this the same thing as this? If you take the derivative of the magnetic flux, can you just bring this derivative with respect to time inside and put it on the b? In general, you can't do that. And I just want to make an example to show why you can't do that in general. Let's say you have a rail, a wire, and another rail that's a wire, and then you have here another wire that's perpendicular to them, and it's moving with some velocity v. And so there's a closed circuit here. You connect this to an ammeter, so you can see if there's current going through here, and you put a magnetic field going upwards perpendicular to this area, and this rod moves to the right with a speed v. So the area is increasing with time. The magnetic field value stays the same, but the area, the magnetic field value actually doesn't have to stay the same. We're going to take the general case where the magnetic field can change with time and the area changes with time. So what in general is the derivative of B times A? B times A is the magnetic flux in this particular example. What's the derivative with respect to time of the product of these 2 quantities? Well, the derivative is the first times the derivative of the second with respect to time plus the second times the derivative of the first with respect to time. The product rule. So this term is the term that we took before. This is the change in the magnetic flux due to the change in the magnetic field itself. The magnetic field, if it's changing with time, then this term is non-zero. And then you have another term here that has B times dA by dt. This is the change in the magnetic flux due to the change in the area. Because the magnetic flux is not just B, or it's not just A, it's B times A. And this product could change due to the fact that B changes with time, or if the area changes with time. Both things could happen also. So in general, this term, you can't just equate it to this term. They're not in general always the same. If the area is changing, if the wires are moving. That's why we were very careful to mention that in our case, the first case we're talking about the case where the wires are not moving. So if the wires are fixed and this is not moving, then you get 0 for this term. And in that case, then this derivative with respect to time, you can take it inside the integration, and it's the same thing as d by dt of the magnetic flux. So this relation is only true if the wires are fixed, if there's no movement of this wire. So that means that the magnetic flux in general, it can change due to two reasons. One reason, if the magnetic field is changing only, or if the area is changing. And that's why we've separated this chapter into two parts. The first part, we always label it that the wires are fixed, and we only change the magnetic field. The second part is if the magnetic field is constant and if the wires move only. And then we're going to do the third part if both things happen at the same time. So the magnetic field could be changing with time and the wires move also. That will be a more general case. So that means that this derivative, we cannot bring it inside and put it on the partial b to make it partial b by partial t, except if the contour is fixed and not changing shape. This contour has to be fixed and not changing shape. If the area is changing, then there'll be an extra term. So then these two things won't be equivalent. So we can make this trick by taking the derivative with respect to time, take it outside only if the contour is fixed and not changing. So that's why we can then rewrite the Faraday Maxwell equation, rewrite it in this form. Integration of E dot ds, we can write it as minus d by dt of the magnetic flux. So we can do this as long as the contour is fixed. So this is the form of Faraday's law that we're going to take. We're going to try to write everything in terms of the magnetic flux. It's much easier to do that, and that's why the textbooks, they always write this relation in terms of magnetic flux, not in terms of partial b by partial t, because partial b by partial t is something mathematically a bit more complicated to deal with. So if the magnetic flux is not changing with time, then the right hand side is 0. Then in that case, integration of E dot ds is 0, and then you have only the case where you have a conservative electric field.